Today we're going to look at practice problem 2 from week 6. This one focusing on friction. So as always, let's start by reading the problem. So we have a pair of identical 5 kilogram wooden blocks pulled along a horizontal wooden table by a string. We're told a 1 kilogram rubber cube is placed on one of the blocks and a 1 kilogram aluminum cube is placed on the other. We are given all of the coefficients of friction for wood on rubber, and wood on aluminum. And what we want to know is how hard does each block need to be pulled before the cube on top of it starts to slip. So let's draw our sketch. So here's our table. We have the mass of the wood is 5 kilograms. Let's make this one the rubber one. So this is the mass of the rubber, is 1 kilogram. And this is pulled with some force that the string exerts on the wood. And then the aluminum is going to look very similar. Mass of wood, mass of aluminum, 1 kilogram. This is 5 kilograms. That's the force the string exerts on the wood. And because we're only caring about the moment when these start to slip, we don't need to draw multiple times in our sketch. Just this is the moment when they start to slip. So let's organize our thoughts here. So let's think about what happens before they slip to understand what's really going on here. So if I have one block resting on top of another one, and I pull this block, why does the other block come along with it? Why don't I just pull the bottom block out from underneath the one on top? And the answer is friction. If there were no friction, then this top block would stay exactly where it is. The bottom block would get pulled out from under it and it would just fall down. So there has to be some friction component of the force that the bottom box exerts on the top block in order to make it move together. So remember, friction opposes sliding. So if this top box were moving on the top, then it would be sliding against it. And friction wants to prevent that. So this will start to slip. The box on top. Oh, there's a drop of water on my tablet. That's why that screwed up. The box on top will start to slip when the friction needed to keep it accelerating with the bottom block exceeds the maximum, the threshold static friction. And that is our equation for the maximum static friction. So this is what's going to happen. The box on top will start to slip when the friction needed to keep the accelerating with the bottom block exceeds the maximum static friction. So let's draw the force diagram for that moment. And let's draw it for the top block, because that's the one that's going to accelerate. We would need to know what acceleration can this maximum force of friction give that block. So here's the force diagram for the top block. What are the forces exerted on the top block? Well, I'm sorry, in the wording of the problem, this was called the cube, so that we can call the thing underneath it the wood. So the wood is interacting with the cube, and the earth is interacting with the cube. Notice that the force that the string exerts is on the wood, not on our cube. So this is going to be the force the earth exerts on the rubber cube. And I can draw another one over here. This will be the force the earth exerts on the aluminum cube. And then my friction is going, or the force the wood exerts on the rubber is going to go in this direction, because it needs to have that friction component that's accelerating the cube forward, and it needs to have a normal component keeping the rubber from falling through the wood. And I can see the same thing. It's the friction component. That's the normal component of that force. And notice that I drew the friction component for the aluminum a little bit smaller than the friction for the rubber. And that's because, if I remember correctly from my table, the coefficient of friction for wood on rubber is 0.7, and for wood on aluminum, it's 0.22. So my expectation is that I should get less friction for the aluminum than the wood, or than the rubber. And as always, when I draw a force diagram, I'm going to write out Newton's second law in all of the directions that I can. So the acceleration in the x direction is the sum of the forces in the x direction divided by the mass. In this case, it's the mass of the rubber cube, is equal to the sum of the forces in the x direction are just that friction component. And the acceleration in the y direction is the sum of the forces in the y direction divided by the mass. And the sum of the forces in the y direction are the normal component of that force plus the force the earth exerts on the rubber divided by the mass of the rubber. And this will look exactly the same. Acceleration in the x direction is equal to the sum of the forces in the x direction divided by the mass of the aluminum is equal to the friction component of the force the wood exerts on the aluminum divided by the mass of the aluminum. And in the y direction, the sum of the forces in the y direction divided by the mass of the aluminum is equal to the normal component of the force the wood exerts on the aluminum plus the force the earth exerts on the rubber is equal to m times r. So we need to find the acceleration when the friction component is at its maximum. So that friction component is equal to, so I can use Newton's second law here. So the acceleration in the x direction is equal to mu times the normal component times the mass of the rubber, and acceleration in the x direction is equal to mu times the normal component times the mass of the aluminum. There we go. And now I can use what I know in the y direction. So in the y direction, I know the acceleration in the y direction is equal to 0. So the sum of the forces in the y direction is equal to 0. And this is true for both of them. I should probably put that in the middle, but oh well. So that means that the normal component, which notice I need for this equation, I don't necessarily know what that is ahead of time. You might have suspicions about what it will be, but you should always rigorously prove that it is what you think it is, because sometimes it won't be. Plus the force the Earth exerts on the rubber is equal to 0. Same here, the normal component plus the force the Earth exerts on the aluminum is equal to 0. The way we calculate the force the Earth exerts on an object is always m times g. So the normal component is equal to negative mg. That equals 0. Then plus negative ma times g is equal to 0. This is 1 kilogram. This is 10 newtons per kilogram. This is 1 kilogram. This is 10 newtons per kilogram. So the normal minus 10 newtons is equal to 0. So for both of them, the normal component is positive 10 newtons. That makes sense because we expect the force to go upwards. So now I can plug this back in here. So the acceleration in the x direction is the mu times the normal force. I'm just going to rewrite this so I don't forget. R ax is equal to mu Fn over ma. So this is 0.7 was my coefficient of friction for the rubber, times 10 newtons divided by 1 kilogram, and I believe it was 0.22. 0.22 times 10 newtons divided by 1 kilogram. .22. Good. So the maximum acceleration under static friction for the rubber, so this, now I'm going to call this the acceleration of the rubber, this I'm going to call the acceleration of the aluminum. This is 2.2 meters per second squared, and this is 7 meters per second squared. So if I pull both of these blocks, the aluminum will start to slip when the acceleration is 2.2 meters per second squared, and the rubber will start to slip at 7 meters per second squared. So I can do a quick evaluation. Does this pass the smell check? And it does. I expect the aluminum to slip first, because the coefficient for rubber is greater than the coefficient for aluminum. But I wasn't asked for the acceleration. I was asked for the force that has to be exerted on the string, or by the string, in order to make these slip. So what I want is that force. And notice that I can't get that from just the force diagrams that I've drawn, because I've only drawn the force diagram for the cube on top, and the string is not pulling on the cube on top. So I could draw a force diagram for the wood on the bottom, the wooden block on the bottom. But that's a little bit more complicated. I'll do it for evaluation and so you can see it. But when I am solving this problem, I'm going to pick a system that consists of both the block and the cube. And I can do this because they're accelerating together. Up until they slip, they have the same acceleration. So I can treat them as a single object moving with a single acceleration. Sorry. And the reason that I want to pick this system is that it makes the forces the cube exerts on the block and the block exerts on the cube, those forces go away if they're both part of my system. So the only forces I'm left with are the force the earth exerts on the system, the force the string exerts on the wood, and the force the table exerts on the wood, rather than having to deal with this force in between the wood and the cube. So now, force diagram. For the system consisting of block and cube. And I'm only going to draw one force diagram. I'm not going to draw the same diagram for the one with the rubber cube and the one with the aluminum cube. We have seen that they are the same. So as I said, the objects interacting with this system are the string, the earth, and the table. Now let's see. So I know the earth pulls down, and I'm going to say this is the force the earth exerts on the system. And the string pulls this way. I'm going to say this is the force the string exerts on the system. If I called this the force the string exerts on the wood, I'd be okay with that. But since I use system here, I might as well use system here. Now what about the table? So the table, there's also friction between the wooden block on the bottom and the table. And that friction is going to oppose the sliding of the block along the table to the right. So that friction is going to go that way. So that's going to be the force the table exerts on the system. And as usual, I can draw its components. This is the normal component. This is the friction component. And now let's get Newton's second law out of the way. So the acceleration in the x direction, which depends on which of the blocks I'm looking at now, because I've got the two accelerations earlier, is the sum of the forces in the x direction, mass of the system, is equal to the force the string exerts on the system plus the friction component of the force the table exerts on the system, divided by the mass of my system. In the y direction, this I know is 0. I might as well put that in right now. Means that the normal component of the force the table exerts on the system plus the force the earth exerts on the system is equal to 0. That's unnecessary. And I'm leaving off the mass here because equals to 0. I just multiply both sides by mass. Mass goes away. I can always say this. Okay. So now, this is the force that I'm trying to find right here. So let's set up Newton's second law, or let's rearrange this Newton's second law. So the force the system exerts, or the string exerts on the system, plus the friction component is equal to the mass of my system times the acceleration in the x direction. Keeping in mind that the friction here, now I'm going to define this way as positive, is negative mu times the normal force, or the normal component, is equal to the mass times the acceleration in the x direction. It's equal to the mass of the system times the acceleration plus mu times the normal component. And here I have to do the same thing I did before. I have to use what I found in the y direction. I've already made my life a little bit easier here. So Fn plus negative, because it goes downwards, the mass of the system times g is equal to 0. Fn is equal to the mass of the system times g. The mass of the system is the combined mass of the 5 kilogram block and the 1 kilogram cube. So this is 6 kilograms. This is 10 newtons per kilogram. This becomes 60 newtons. And I can plug this in here. So now I can split this for the rubber and for the aluminum. So the force the string has to exert on the system is equal to mass of the system, which is 6 kilograms, times the acceleration for the rubber was 7 meters per second squared, plus the coefficient of friction between, this is the friction, remember, between the wooden block and the wooden table, and this is sliding, this is accelerating, so I need to use the kinetic. So this is the 0.2. 0.2 times 60 newtons. I'm going to see the same thing over here. The force the string exerts on my system is equal to the mass of the system times the acceleration. This acceleration was 2.2 meters per second squared, plus the coefficient of friction, 0.2, times that normal component, 60 newtons. 0.2 times 60 is 1.2 is 12. So the force the string exerts on the system is equal to 6 times 7 is 42. I should probably check my math, but I'm pretty sure that's 42. Yes. .42 newtons plus 12 newtons is equal to 54 newtons. So 6 times 2.2 is 12 plus 1.2, 13.2 newtons plus 12 newtons equal to 25.2 newtons. So now, does that seem reasonable? These two systems have the same mass, but the one with the aluminum block needs a much lower acceleration, so it makes sense that I don't have to pull as hard on it. But there is an empirical way. Keep in mind the systems that I've used so far. I've done a system consisting of the block and the cube, and I've looked at a system consisting of just the cube itself. In order to check my work, what if I look at a system of just the block? I should be able to get that same answer using that system that I haven't used yet. So let's do that. So evaluate by analyzing the block system. So let me redraw a diagram here, just so that I don't have to keep going up. Let's think about the forces. So we saw from our earlier force diagram that the wood is pushing on the block, and I'm going to use the rubber block here. The wood is pushing up and that direction on the cube, which means by Newton's third law, the cube is exerting that force down and back on the wood. So if I draw my force diagram, so there's the wood is my system, the string is exerting a force, the earth, I don't know what that was. The earth is exerting a force, the cube is exerting a force, and the table is exerting a force. So let us draw this force diagram. So the earth on wood goes straight down. We said the cube pushes down this way. This is the force the cube exerts on the wood. The table is going to push in the same direction it was before, up and back. So this is the force the table exerts on the wood. And then this is the force the string exerts on the wood. Do you see why I saved this one for my evaluation? This is the most complicated of the force diagrams. We have 4 forces. 2 of them are at angles. So I can break these both into their components. So this is the friction component from the cube. And this is the normal component from the cube. And let me get a different color, very different color. This is the friction component from the table. And this is the normal component of the force the table exerts. And now I can set up Newton's second law. I'm going to use the full space because I see a lot of forces here. So acceleration in the x direction is equal to the sum of the forces in the x direction over the mass, the sum of the forces in the x direction, or the force the string exerts on the wood, plus the force, the friction component from the table, plus the friction component from the cube over the mass. And these are all things that I know. So the acceleration in the x direction, and again, I can split this into rubber and aluminum. Sorry, forgot my words. So the acceleration for the rubber is 7 meters per second squared. It's equal to the force that I found for this is 54 newtons, plus the friction from the table. Oh, well, this I don't know. I know the friction component for the entire system. Is it different? Well, I don't think it can be. So the friction component from the table was 12 newtons. The coefficient of friction times the 60 newtons plus negative 12 newtons plus what's the friction from the cube? Well, that is this force that we found up here. The 0.7 times this, so that's 7 newtons. Plus negative 7 newtons divided by only the mass of the block this time, 5 kilograms. So 7 meters per second squared is equal to 54 minus 12 is going to be 42 minus 7 is 35 newtons divided by 5 kilograms does in fact get us 7 meters per second squared. So that checks out. Now let's do the same thing for the aluminum. So it might be a little bit harder because it involves fractions. 2.2 meters per second squared is equal to this force was 25.2 newtons plus this friction was still 12, negative 12 newtons plus the friction between the cube and the wood. Again, I have to go all the way back up. This was the 0.22 times 10, so 2.2. Negative 2.2 newtons divided by 5 kilograms. So let's see. I'm going to subtract the 2.2 first, just to get rid of that pesky 0.2. So 25.2 minus 2.2 is just going to be 23 newtons minus 12 newtons is 21 newtons divided by 5 kilograms. 21 divided by 5 should be 2.2. And I will never do this. Oh, I'm an idiot. 23 divided by 12 is not 21. Sorry, 23 minus 12 is not 21. It is in fact 11. That would explain things. So 11. This is probably not going to read. Oh. Value, we get 2.2. 2.2 meters per second squared. And so notice, the reason this is such a good evaluation is because I'm not plugging my number back into the exact same equation that I used. I'm plugging it into a completely different system that I hadn't analyzed before. That's much stronger. If I had, keep in mind that I did this all in my head because I did not think to bring my calculator with me when I was solving this. So had I done my math incorrectly here, this would have had a very good chance of catching that. So I can be pretty confident in these results. All right, thank you.